When you're ready, I can start.
Oui, c'est bon.
C'est bon. Parfait. Merci. 8 minutes late. So good morning, everybody. We're only 8 minutes late. That's great, I think. My name is Eleonora, and I'm very happy to chair this first session of CHESS 2022, track number 1, which is about tools for side channel analysis and cryptanalysis. So I suggest that we begin with the first paper entitled Semi-Automatic Locating of Cryptographic Operations in Side Channel Traces. The talk will be given in a video format that is provided by the speaker, Jens Trautmann, that will be available online to answer your questions later. So let's go.
Hello, my name is Jens Trautmann. I'm from the FAU in Erlangen-Nürnberg, Germany, and together in cooperation with the KU Leuven, I want to present you our topic, which is the semi-automatic locating of cryptographic operations in side channel traces. Let's quickly start with the motivation. So there are several side channel attacks that work on real-world devices, for example, on iPhones, single-board computers, IoT devices, and the goals of all of those attacks are that we want to retrieve keys or implementation details, and the requirements are always that we have some recording of a side channel. Here we have a recording of an AES, and we also want to have an associated plaintext or ciphertext. And then an easy example for an attack scheme is that we could use correlation power analysis, where we correlate the Hamming weight of, for example, here the first plaintext byte with every single point in all of those traces. And if it correlates with the power usage, then we know where the plaintext was used. Of course, this can also be used with intermediate values of the cryptographic operation, and then we can also get the key from this. What is the most important thing here is that all of those traces need to be aligned. So they need to start at the same point in time. And therefore, we need to exactly know where they start and where they end so we can align them. In the real world, if we have a device under test here and an EM probe that transfers its electromagnetic signal to a digitizer or oscilloscope that can then put this onto a PC, we get such a data stream. And the problem is that we don't really know where those starting points are that we definitely need for any kind of attack. And one remedy for this is, for example, this trigger box that was presented by Beckers et al. In 2016, and what this does is that we can compare a previously obtained waveform template, and this is the template pattern of a cryptographic operation or the prologue of one, and we will compare the incoming data stream to this template, and if it is similar enough, we know that a cryptographic operation is happening on the trace, and then we can get single traces of each and every of those cryptographic operations, here marked by those blue lines, to the control PC, which then can do the attack afterwards. But you have to have such a waveform template up front, which is why an evaluator has to go through such a large trace and find one occurrence of a cryptographic operation that can then be used as a template. But this going through the trace and finding this pattern can be a pretty tedious task, which is why we wanted to automate this. And let's first go over the high-level overview of this method. So first we want to identify one cryptographic operation in a larger side channel trace. So here I have one example of an AES 128, and we will only focus on round-based ciphers, as here we can find patterns that are characteristic to those. So here for AES 128 we have 10 rounds, and 9 of those rounds have the exact same operations but with different data, and this also shows in the side channel trace. So here we have 9 rounds that look similar to each other at this starting index I, and an evaluator would go through and find this recurring pattern and say, okay, at this starting point a cryptographic operation should start because there are those recurring rounds. And we want to do exactly that, but automated. So we will go through every index and then calculate the similarity. And the more similar those rounds are, the more probable this is the start of one cryptographic operation. Afterwards, we will generate a CO template from that starting index and then use this CO template, like in the slide before, to find all the trace segments which correspond to other occurrences of the same cryptographic operation. But of course, with different data. And if we have all of those starting points, we can even refine the CO template to get rid of the noise. But this is optional and only needed if we have a lot of noise on our traces. Let's go a little bit deeper into this method and to see how can we calculate the similarity between the rounds algorithmically if we know the round pattern length W. So we will go through each index in this trace T, and for all starting points we will dissect this trace part into the different chunks that are then the rounds or the potential rounds. And those all have the same round length W, and we will use an average of those, we can see here in dark blue, and calculate the similarity between this average round template to all of those different rounds that we made this average round template of. And if we have then the highest similarity, because we do this for every trace index, we will then use the highest similarity index as a starting point of a cryptographic operation, and then use this highest starting point to create a CO template, and then find all other occurrences of this cryptographic operation. To do this on an example, we can see here a black trace, that is our power trace, and then we have the green line up here, which is the trigger trace, which shows us where the cryptographic operations are. Of course, we didn't give this trigger trace to the tool. And if we now look at one good start index, remind yourself we do this for every single starting point here. We will again calculate the average round template and then calculate the similarity between all of those rounds. And then we can also do this for a bad starting point, as we have to do it for any point anyway. We can see here the dark blue color is the average round template, and this is not similar to all the colorful lines that can be seen here also. And if we then calculate the similarity, we will see that there are certain peaks, and especially the highest one here with a similarity of 0.85, which here corresponds to correlation. You could also use sum of absolute differences. And this highest point we will use for a new CO template that we will then correlate or calculate the similarity over the entire trace. And here the bad starting point amounts to a quality of 0.37, which is really low and will be not considered as a CO template. So if we take this nice CO template and correlate it over the entire trace, we will find very distinct points here, which I mark with the green triangles, and those points are exactly the starting points of every single CO. But the problem here is that we supposedly know the round length pattern. But what if we don't? Well, then we could go through all reasonable widths W that we can calculate and determine, as we did before, a CO template for this width, and then also calculate the similarity between this CO template and our entire trace. But to do this, we have certain requirements that are also valid for if we know the round length W. We need to know the trace and the sampling rate we recorded it at. We also need to know the device clock frequency, so the frequency of the device. Otherwise, we can't really get different widths or possible widths, because we need to find out how many samples one clock cycle has. And then we also need to know the number R of successive and identical rounds that are part of this cryptographic operation. And what we can then do for all of those widths is filter the correct width out by checking out how many possible starting points there are. And we can do this based on the shape of similarity that we will see on the next slide. And if this number of possible starting points that we found is equal to the number of cryptographic operations in the trace, we can say that this might be a reasonable or a possible width that we can use further on. And this, of course, has the requirement that we need to have a known number of cryptographic operations in this trace, which is then n. So this is our new requirement if we don't know the width W. So let's go. How can we find out if one starting point is actually a starting point of the CO? Here in gray we have the trace, and the green lines here are the starting points of one cryptographic operation, which is not a knowledge of the tool currently. And then we already completed the first step where we found a potential CO template. Now we calculate the similarity of this template over the entire trace, and what we can see here is this similarity curve. As the maxima don't really line up with the starting points, we have to filter this. So there's a moving average filter here, which is parameterized based on the round width W, so we don't have to do this every time, and it is automatically parameterized. And then we can see that the starting point marked in green line up well with the highest points of the filtered similarity curve. If we now look at one specific point here, we can see that there is one high maximum, and then there are several lower maxima here, and we call the main one main peak, and then we have sub peaks behind that. And this structure, this shape here, occurs because we first match all of the 9 similar rounds, because this is AES and we have 9 similar rounds in this trace, and then we have the sub peaks that match 8 rounds here, and then only 7 rounds will match, then 6, and so on and so forth. And because of this shape, we can calculate the number of sub-peaks behind each main peak that is in the width W distance to the main peak. And we use this as a characteristic to say if one peak is actually a start of the cryptographic operation. So we check out the number of sub-peaks for each main peak and then find out how many possible cryptographic operations are there on the trace. If this was a little bit too fast, you can look in the paper and see for yourself how this works. So we did a proof of concept with multiple different systems, and I will just briefly show some of them. The tiny AES on the ARM Cortex M4 was a pretty easy target. You can see here a cutout of a trace, so this is only part of the trace. The green is the trigger trace that we didn't give to the tool, and then the tool found this template here, for example, and the starting points that were 100% accurate, meaning that the starting point that we found is no further than the length of one cryptographic operation in either direction away from the actual starting point. And we also tried this with the hardware AES. This is on the same platform, but with a hardware AES. And then a more difficult target is the ARM Cortex A8, which is clocked at 1 GHz and is located on the BeagleBone Black, which runs Linux. And we executed OpenSSL AES 128 on it. And you can see here one execution of that. And the template that we found is this here. And here you can really see the round structure of the different rounds. And then the last round looks a little bit different. More interestingly, we also looked at the ARM Cortex M4, but this time a different model with Mbed TLS and SCA and not AES, which is also round-based and has 64 rounds. But we recorded it one time with an external clock and one time with an internal clock. And the external clock was synchronized with the oscilloscopes, who have really nice recordings, but the internal one has also a little bit of clock drift, which made the recordings a little bit more difficult for the tool to extract. And here we chose the first 16 rounds to compare and to find, and we found all of the starting points after refinement with 100% accuracy for the internal clock, and for the external clock we find them right away. And with Mbed TLS AES 128 on the same target, also with an internal and external clock, we also find all of the starting points. And for the internal one, again, we needed some refinement to find all of them with 100% accuracy. To show that all of the starting points are really accurately found, we created a toy yet realistic example on the ARM Cortex M4 microcontroller. And we simulated that we would have a boot content with 8 kilobytes that is encrypted and is shifted from the non-volatile memory, and it is hashed, and then we have a signature check, and we have those 500 decryptions. So because of the signature check, we can't change the ciphertext that goes into the decryption, so we have to use what we got from here. So the attacker capabilities is that we can read out the boot image from the non-volatile memory. We have the knowledge of the different boot stages, and we also know that there is AES 128 running. Also, we can record a power trace of the entire boot process, which ends up being 250 million samples. And for convenience, I noted here where the different parts take place. So we have hashing here, then the signature check, and then the 500 CBC decryptions. And of course, we can use CPA to attack this, but for this, we need to know exactly where those 500 AES decryptions take place in order to align them. And we wanted to use the tool for that, so we gave the trace to the tool, and we extracted all of the 500 ciphertext from the non-volatile memory. We evaluated then 40 different widths, and the tool considered 3 as plausible, and we can select one after looking at the template that the tool produced and also at the found starting points. And if we use then all of the starting points to create a trace for each found starting point, we can then associate that with the ciphertext that we found on the non-volatile memory and then use CPA directly on this data without any further post-processing or alignment of those found traces. And full key recovery with those traces is possible after only 200. And the unsupervised analysis that we tested here, the 40 different widths, took 2 hours, and selecting the best candidate and doing the attack actually only took a few minutes. And this here is the part then that an analyst has to do, and the other part can be done unsupervised. So we cut down the part of the analyst quite heavily. So to summarize, we presented now our semi-automatic algorithm that can find COs in large side channel traces, and the partly unsupervised analysis helps to search through very large traces without a lot of effort. The functionality is based on meta information, meaning the number of cryptographic operations in a trace, the number of successive and identical rounds are, and the device frequency. But we don't really need a template as we have in other approaches, which means that if we want to re-evaluate the device, we don't need to record a new template because we can just use the same meta information and still find the cryptographic operations. Limitations are, of course, random delays, unstable clock frequency, some dummy rounds that get inserted into the implementation, so everything that messes with the round structure. Our implementation utilizes parallel GPU computation, which means that we are highly scalable, and we can also utilize data centers, for example, to really speed up the process. Also, the open source implementation and the chess artifact is available, and we further also have some Jupyter notebooks which can interactively show you all the steps I just showed you, and you can also access that under the link of this artifact. For future work, we evaluated this technique and method on different architectures, especially FPGAs, and looked at the success rate that we could have if we have noisier recordings of FPGAs, and this was published at the FCCM this year. So this was everything from me. Thank you for your attention. Do you have any questions? You can always write me an email or ask right now. Thank you very much.
So thank you, Jens, for the nice talk. There is time for question. I didn't see any question in the chat. Any question in the room? This is the shyness of the first paper. So I guess I can ask you my questions. So Jens, we can maybe look at him. Yes. So your tool is semi-automatic in the sense that some interactions with the users are necessary. So I wonder how many interactions one may expect.
So thank you. You can hear me well?
Yeah, we hear you.
Yeah, nice.
Everybody hears him?
So the interaction is limited to the beginning and the end, right? So you can try out the different widths automatically, but first you have to put in all the information that the tool needs, right? The different widths that you want to test at the trace, and configure everything. And then at the end, you, again, as we showed in our secure boot example, have to get the correct width out of the candidate it's selected, and then use that. So there is just interactions at the beginning, at the end, and you can't run it unsupervised completely. Yeah.
Okay, thank you. There's a question from the chat from Jan Breeze. Is it possible to potentially modify the method to account for non-uniform W?
So, yeah, so if the width is different if you mean that there are different, for one operation, you have different widths, then it is really difficult, I guess. You could, if you had, for example, random operations, maybe dynamic time warping would be an option to account for that. But we didn't look into that for now. Yeah.
Okay, thank you very much. So let's thank Jens again. Please. So I'd like the next speaker coming on stage, so Chao Sun. So Chao Sun is gonna give a talk about his work, his and his co-authors' work. Guessing meets improved lattice attacks on ECDSA with nonce leakage.
Okay, thanks for the introduction. This is joint work with Thomas, SP, and my advisors, Mehdi Tibushi and Masayuki Abe. And to start with, here's the roadmap of the signal signature. So to send a message in, so first we choose the random K, which we will call the nonce. And let R equals to the K where G equals G to the K, where G is the generator of some group, and E equals the hash of the R concatenated with the message L. So the signature equals the K minus alpha times E, where alpha is the standing key. For signal signature, the careless implementation easily leads to K recovery. Okay, so for signal signature, we should never reuse the same nonce, and due to the linear relation between the nonce and the secret standing key, we can easily recover the standing key. And according to BBC News, 10 years ago, the iPhone hacker publishes the secret Sony PlayStation key, mainly because the engineer made a mistake that he's using the same nonce for every signature. And the reverse, the partial nonce leakage can lead to K recovery. For example, the attacking 250-bit, 256 bits ECDSA with 5 bits nonce leakage is pretty easy. And there are a lot of practical examples. For example, there are attacks on Android phones and on cryptocurrencies. For example, in the second one, the attacks on cryptocurrencies, they also found that in many of the Bitcoin transactions, the pseudo randomness is generated as a 64-bit randomness. So only having several signatures can recover the secret standing key. And generally, there are two ways to attack the speed biased nonce ECDSA, which is just a variant of the signal signature. The original approach to solve is the Blasian-Butcher attack, which rely on the free analysis techniques. And the lattice reduction also provides an attack techniques, which is our main focus in this work. And for lattice attacks on ECDSA, 20 years ago, Graham and Smart, and later Wien and Spalinsky found that attacking ECDSA with nonce leakage reduces to a lattice problem. However, when the nonce leakage is very small, the lattice attacks become more difficult. In 2013, Liu and Wei attacked 160-bit DSA with 2-bit nonce leakage using EKZ2 with the block size 90. And at Eurocrypt 21, Albrecht and Hellinger used the GCK together with the idea of predict sieving to break new records. And here is these two tables are the reported results of the attacks on ECDSA. And the first one is the lattice attacks on ECDSA. As we can see in the table, now lattice attacks can deal with 160-bit modulus with 2 bits nonce leakage and 256-bit modulus with 3 bits nonce leakage and 384 bits with 4 bits nonce leakage. And by comparison, the Blasian-Butcher attacks can deal with a bit small nonce leakage. For example, it can deal with 160-bit modulus with 1 bit nonce leakage and 256-bit modulus with 2 bits nonce leakage. And here is a comparison of the Bayesian bilateral attack and the lattice attacks. So generally, Bayesian bilateral attacks can deal with small mass leakage, but of course, the cost is it uses more signatures as input. For typical parameters, the Bayesian bilateral attack use 2 to the 27 signatures, and the lattice attacks use around 100 signatures. Another difference is that at each iteration of Bayesian bilateral attack, some bits of the signing key is recovered. With more non-bits of the signing key, the attack becomes easier and easier. But the lattice attacks are generally all nothing, which means that, okay, so when you succeed, you get the full signing key, and when you fail, you get nothing. And so the Liu Wing and average the Hellinger attack at improving the lattice reduction algorithm itself. In this work, our starting point is slightly different. So we are trying to understand some kind of relation between the Bayesian bilateral attacks and the lattice attacks, which has been mentioned by Tibushi at ECDSA and also Hellinger at the lattice cryptography camp. And concretely, we can ask several questions. First, the lattice attacks on ECDSA are generally all nothing. So if some bits of the signing key is known, does it make the attack easier? Secondly, can we exploit the spatial structure of the lattice? And thirdly, by comparison with the Bayesian bilateral attacks, if given many more signatures, can we improve the lattice attacks? We'll give positive answers to these questions and do practical experiments following the Minowa. And here I skip some technical details and claim that the lattice attacks on ECDSA amounts to this problem. Given details of the signatures are ISI assigned with bias nonce, we construct a TI-UI such that the alpha TI minus UI plus CIQ is between 0 and Q over 2 to L, where alpha is the signing key and L is the number of leakage. Then we construct the following lattice, and this vector U is our target point, and the hidden closed lattice point in this way. As we can see, the last coefficient of the V is alpha, which is our signing key. So if we recover V, then we recover the signing key. Then we can solve this lattice problems by neural spring algorithm or canal embedding method. And let me introduce some intuitive ideas to improve the attack. So if we, for example, if we consider the case of BDD or CAP, denotes lambda 1 as the length of the shortest vector in the original lattice, and E as the distance between the target vector and the lattice. Intuitively, in order to improve attack, we want to increase the ratio between lambda 1 and E. Or equivalently, if you view it in the embedded lattice by canal embedding, it becomes a unique SVSP instance, and the goal is to increase the gap between lambda 2 and lambda 1. To increase lambda 1, according to Gaussian heuristic, the goal is to increase the volume of the lattice. Recall that the lattice we construct is this one, and the target vector is this, and the hidden lattice vector is this, and denotes the difference vector between them as E. According to the property of those inequalities, each coordinate of the E is upper bounded by Q. And if we observe the structure of this lattice, if we want to increase the volume, we can just modify the factor 1 to, for example, to the 100. And in this way, we increase the volume by 2 to the 100. However, there is a serious problem that the hidden lattice vector will not be close to the target vector anymore, because the hidden lattice vector is this, becomes this, and the last coefficient becomes 2 to the 100 times alpha, which is very large, as I mentioned. As I mentioned, so each coefficient of the difference vector is upper bounded by Q. So this 2 to the 100 alpha is very, very large. And so it means that it's not quite meaningful. And the attempt 2 is that, okay, following the ideal Bayesian bilateral attack, can we enumerate some bits of the signing key and improve lattice attacks? For example, we denote alpha with equals to the alpha1 times 2 to the c plus alpha2. And then we substitute alpha with this one in the inequalities. And then we get a new instance for the alpha1, which is some most significant bits of alpha. However, the remaining instance seems to be as hard as the original one for lattice attacks, so which also means that it's not quite meaningful. But perhaps interestingly, if we combine these two attempts, something interesting happens. For example, if we increase the volume by 2 to the 100 and just assume that the standing key has 60 bits, and then 2 to the 100 alpha is upper bounded by 2 to the 160, which is roughly Q. Then we have increased the volume of the lattice by 2 to the 100, and the difference vector, the Euclidean length of the difference vector hasn't changed. So more generally, we can enumerate the standing key by C bits and increase the volume of the lattice by a factor of 2 to the C. And the length of the difference vector doesn't change, thus we can improve the attack. And we have some other similar ideas. For example, we can enumerate additional bits of the nonces on top of those that are already known. And for example, suppose that we are in the context of a 160-bit group with 2-bit nonce leakage, and we try to enumerate the third LSB of the nonce. However, if we enumerate one more bit for all the signatures, it will become a huge computation, but we can do it for part of signatures and construct a hybrid lattice. For example, we can guess one more bit for 20 out of the 100 signatures and keep the other 80 signatures unchanged and construct the hybrid lattice like this. And then we perform the lattice attacks on the new matrix at the cost of 2 to the 20 operations for guessing bits. And here are some advantages of our guessing bits attacks. First, it is very easy to simulate. For example, we can assume that we have guessed the correct bits for self-generated instances. This can save a lot of computation costs and make the estimate of cost very easy. By comparison, if you directly use PKZ with high block size, it will be a very huge computation cost. And it is very easy to parallelize the attack. And also we can because we are constructing batch CVP instances, so we can use the batch SVP and the CVP with pre-processing techniques. And actually, this is a good scenario to test those algorithms. And besides, it is compatible with all those existing techniques for improving these attacks, and it's quite straightforward to combine our ideas with those techniques. And due to time limit, I will introduce some additional contributions, but roughly mention them. We have one more variant of attacks, which is utilize many more signatures to improve the lattice attacks. And we gave an explanation of the gap between the CVP and SVP approaches, which has been observed in the Minawa paper. And we also have a discussion on choosing the Canaan embedding factor. And we also have a theoretical analysis of the lattice attacks on ECDSA. And here is our experimental results. I'll briefly introduce them. Here, the left one is the guessing bits of the secret key, and the right one is guessing bits of nonces. And as we can see in these figures, for example, for 256 bits with 3 bits nonce leakage, if we enumerate and guess 20 bits of the secret standing key, and then we roughly get like a 30% success rate. And the algorithm we are using is just PKZ30, so which means that the computation cost is 2 to the 20 times PKZ30, which we think is quite a reasonable time. And sorry. And we also did some experiments on TPM fail data sets following the work of TPM fail and Monero. And with only 800 signatures, we are able to recover the signing key. And finally, here is a summary. We propose new ways to improve lattice attacks on ECDSA, which is get some bits of the secret key or the nonsense. This solves difficult cases for lattice attacks, and it is very easy to simulate and parallelize it. And the experimental results validated our ideas. And that's all for my talk. And thank you for your attention. And I'm happy to take questions.
Thank you very much for this talk. So actually you saved 1 minute. So we have 1 minute extra for questions. Nobody? Okay. On the Zoom, no more. Okay. So I have some short questions. I was wondering, in order to use your approach, has the noise leakage to be exact, or you can somehow deal with some probabilistic values for the leaked bit?
Sorry.
So the leakage nonces have to be exact, or you can deal with probabilistic values?
Oh, well, so yeah, in general, lattice attacks are quite sensitive to the leakage errors. So like if you have like 100 signatures and maybe if 10 of them are incorrect, maybe I guess the success rate will become very low.
Okay.
Yeah.
Okay, thank you. Any question now? No? So actually I wanted to ask you, there is a paper that appeared at Crypto 2020 that suggested a methodology to inject extra information that they call hints in order to get an easier lattice reduction. Do you see any relation between your approach and theirs?
Which one?
The Crypto 2022, which was about injecting hints, information hints like, don't you see the...
So what's the title of that?
Yeah, that's a good question. Somebody has... Pardon? Oh, we can't hear you. LWE with side information. LWE with side information? That was...
Oh, you mean
Melissa is here.
By Ducato?
So it's LWE with sign information. The idea is to add some extra linear equations that you have on the short vector that you're looking to find. So I don't know if it applies here.
Yeah, so well, I think those two type of lattices are somewhat different because the LW lattices are like a random curve lattices, and in our case, the HMP lattice is kind of life cycle like, so it's quite different, and their analysis relies on the Gaussian Gaussian distribution, and in our case, it's kind of a uniform distribution, and it's kind of well, maybe the general idea is somewhat related, but for most cases, I guess it's kind of quite different.
Okay, thank you. Any question now? Not at all. So thanks again. Ciao.
Thanks.
So I introduced the third talk, which is about side channel attack on string ciphers, a 3-step approach to state key recovery. And the talk will be gently given by Dirman Tojap.
Hello, can you hear me? Okay, so welcome everyone for the presentation and thank you for the introduction. For this talk, I'll be presenting our recent work, side channel attack on stream ciphers. Basically, we are using three-step approach to recover the state of the key bit. This is the overall outline for the presentation today. So first, we start with the introduction by defining our problem formulation. So the idea is that given a stream cipher, since most of the work being done on block cipher, can we design a generic framework which can recover the secret information given a noisy side channel traces? From what we observe to our knowledge, most of the work that has tried to address this problem are carried mostly only on initialization phase, or they are using multiple IVs for noisy traces. Hence, the proper framework to address this question in the pseudo-random phase of a stream cipher using a single IV on noisy traces is still missing. So following that, that's our contributions as follows. We design a generic framework which works as a state bit recovery or key recovery for NLFSR-based stream cipher or other cipher with a similar structure. In this case, basically, we are combining multiple tools using machine learning ML, mixed integer linear programming MLP, satisfiability modulo theorem SMT within a single framework. So then, upon the construction of the tool based on these different tools, the attacker can fit in the traces and he can get the secret back. These tools work in both initialization and pseudo-random phase, and also even in the presence of noise. It can be carried out in a single key IV environment, and we have tested it in a Trivium cipher implemented on a 32-bit ARM Cortex-M2 on Arduino DUI. To recall, basically, we compare with previous work. As you can see, for our work, we are there's only, besides our work, there's only one which is working on pseudo-random phase, whereas everything else is working on the initialization phase. For the noise, basically, if you are working on the noisy traces, basically you will require multiple IVs, and then if you require single IV, it's basically a noise-free setting. So in this case, we try to address this problem. So this is the general idea of our framework. So we basically try to first give a traces, and then we predict the Hamming weight, Hamming distance sequence or using machine learning. And then finally, we feed this information to our tool to retrieve the secret. So we use SMT instance to return a solution within reasonable time for unknown state of the key. So this is the generic framework. So it's basically a profile setting. First, we have a device. We collected the traces. We train a machine learning model. Then we simulate the cipher. Basically, what we mean is we inject the noise into this Hamming weight, Hamming distance information. Then we compute the error tolerance limit of the SMT, which we'll explain later. This is the offline phase. We get this train model and the error tolerance. And then for the online phase, we have another device under target. We collected the traces. We pass it to the trained machine learning model. It will predict a Hamming weight, Hamming distance sequence. Then we do a correction using MLP, which we'll explain later again. Then we get a corrected Hamming weight, Hamming distance class. Then we pass this to the SMT solver, and then this SMT solver will give us the secret information back. So this is the overview of our approach. By error tolerance is basically given original actual Hamming weight. When we get a predicted Hamming weight, the error tolerance epsilon defines that our predicted Hamming weight is successful if it's within the plus minus epsilon within the from the original Hamming weight value. So as mentioned before, we train the machine learning to predict the sequence of Hamming weight and Hamming distance. However, we know that machine learning is not always 100% giving 100% accuracy. So, and this is a problem since our SMT solver require 100% correctness. In this case, then we use another tool, which is mixed integer linear programming, MLP, which is basically optimization problem. You have an objective to solve, and then you subject to you have a certain constraint. So we use this to correct the predicted sequence. So we use a Gurobi as MLP solver in our case. Once we got the output of the predicted sequence of the Hamming weight and Hamming distance, we pass it to the SMT, which is a generalization of the Boolean set. This basically is a solver which can involve real number, integer, bit factors, and etc. So we use Z3 as a SMT solver for our tool. Our target function is a stream cipher trivium, which comprises of three NLFS, of size 93 bits, 84 bits, and 111 bits. In total, they construct like 288 bits for this in the pseudorandom phase. The secret key and the IV are both 80 bits, and the state update function is invertible. So if you obtain the state bit of 288 bits, it can be used to reconstruct back the secret key. This is our brief information about our setup. So this is for the measurement, we use the following setup. We implemented the target function on ARM Cortex M3 in assembly. It's mounted on Arduino DUI. We use a rescuer high precision EM probe for collecting the traces. We perform a grid search. So in the picture is shown the optimal position as per our knowledge. We got a SNR of 3.3. We collected 2 to the power 21.17 traces. This is used in total for training, validation, and testing. So for the we consider MLP, since this is the simplest form we can use. We consider a supervised classification problem. Since this is a Hamming-Weight leakage model with 32-bit microcontroller, we have a 33 classes, and we train it on the MLP classifier. To give an overview, so basically this is the trade-off between the machine learning accuracy and the error tolerance. So as you can see that if we force it to be exact, tolerance equal to 0, the machine learning accuracy is only 39.3%. However, as we increase the tolerance, the so-called accuracy increases. However, if we there's a trade-off, if we compare it with the SMT, the higher the tolerance, the solving time is increasing. So here we have to take a trade-off. So we take epsilon equals 3, which provide a good speed accuracy trade-off. However, there's still small chances that the classes are predicted incorrectly. So we want to reduce it even further. So we use MLP as a mean tool in between to correct this prediction. So for the MLP model, what we want to do is that we have a sequence of Hamming weights. We want to so-called correct it so that it's closer to the Hamming weight sequence, but it's still near to the predicted Hamming weight sequence. So this is the objective function. And for the constraint, we constructed 3 types of constraint. This is detailed more on the paper. So basically, it's based on the incoming and outgoing bit relation. So for figure A, basically this is based on the cipher construction. You have multiple registers. In trivium case, it's a 3 registers. So for each round, when the function is updated, there's a bit which is going in and bits which is going out. Then based on that, the Hamming weight will have certain properties. If the prediction is incorrect, then the Hamming weight value will violate this relation, and it can be detected and corrected using the MLP model. So we use 2 models. So the first one, as I mentioned, is based on the LFSR itself. The other is based on the implementation on the B. So basically, it's based on the microcontroller. In this case, it has 32-bit register. So the function update also have some relation. So in this case, we combine them into 3 types of constraint, and then we fit this to the MLP to solve. We have implemented it on Trivium, and we run 1,000 experiments. The result, the success rate is shown on the figure below. The success rate at 110 rounds on threshold epsilon equals 3 is 97.6%, taking 3.3 seconds on average. So if we repeat the experiment twice with different sequence of Hamming weight, for example, we take the sequence on this on the beginning of rounds, and maybe we take somewhere others with a different sequence, we combine them, the result, the success rate can increase even further. As we notice that, for number of rounds, as the number of rounds increase, the success rate decreases over time, and the solving time is also increased. So once we get the MLP result, we pass it to the SMT to solve for unknown key or state. So we basically convert the system of equation constraint to system of modular equation, which is supported better in Z3. So we fed all these constraints to SMT solver, and if the Hamming weight class predictions are within the tolerance, the solver will return a solution within a feasible time. Hopefully it's a unique solution. Then we can verify by feeding it back to the cipher, and we check the correctness. If the solution cannot be verified, we basically run the SMT again. This time we increase the number of rounds. So we start with a fixed number of rounds, we increase it, and then we predict the sequence every time if the solution cannot be verified. If the solution is inconsistent, means that the one of prediction is falling outside. So we have to perform a recovery procedure. One of the solution we propose is basically we just measure longer rounds, and then we just use partially some of the rounds. And if the prediction is inconsistent, we just use another part of the rounds for the attack. So this is the result when we tested it on the pseudo-random phase, which this is all the parameter which return the unique solution. So the first one is on the A is basically without the key stream. So we only consider the update function and the Hamming weight. And since we are working on Hamming weight 32-bit microcontroller, so an error tolerance of 3, the result is on the bottom SW32 3 tolerance of 3. And then we can see like for number of rounds 180, the mean time is the shortest, because if you reduce the number of rounds, the SMTs will take much longer to solve. So in this case, yeah, we can manage to recover the unique solution for the without the key stream information. And if we provide a key stream function generation function to the solver, the solving time can be even the number of rounds can be reduced, and solving time is even faster. So to give a summary, basically for Hamming weight model, we can recover the internal state uniquely for the pseudo-random phase. And then for initialization phase, we can predict the with even higher accuracy on a higher tolerance level. Because on initialization phase, you're only solving it for 80 bits instead of the full 288 bit. So we can solve it even faster and only on 80 seconds. We have shown the result for the Hamming weight model. Then we switch to Hamming distance model. For Hamming weight, we have 33 classes. For Hamming distance model, it's just simply we take it further from -32 to 32. So it's a 65-bit model. We tried first on the initialization phase. Up to tolerance of 1, we can recover the state bit without needing any guess. However, as we showed earlier, that for machine learning classifiers, tolerance-wise is not that good, so we have to increase it. But when we increase it further, it needs another key bit guesses. So for previously, we showed that tolerance 3 is good enough, but this time we need 20 bit guesses. For pseudo-random phase, to predict all 288 bits, we will require 140 stage bits. However, it exceeds the exhaustive search complexity on the key bit, which is 80 bits. So this is done by running the experiment like 2 days. So maybe if we increase more time, it might be solved, but we did investigate further. So to summarize, basically this is our framework. We have first offline state to get a machine learning model. We then target the device, another device where we collected the traces. We predict the class using machine learning. We corrected it using MLP. If it's inconsistent, we perform a recovery. Otherwise, we pass it to SMT solver. If there's no unique solution, we rerun it again, and we try by increasing more information, and then we recover the key state or secret state or the key bits. Yeah, so basically our framework, we show that it works for our proposed approach. Another question we are asked before, we have also tried a different variety of SNR by testing on multiple SNR scenario, and then we show that when the SNR go beyond 1.12, the success probability drop to 0. So for our current setting, this is our limit, but we can probably increase it further. This is the future work what we can do. So first is we consider another analytical approach where it might work for less than perfect accuracy. So we can consider it's a hidden Markov model, which maybe can work again by switching it and remove MLP. We can also consider another leakage function. We are only considering Hamming weight, Hamming distance, but maybe another form will be better. And then lastly is improving the ML, since we are using basic ML such that we are using basic MLP. Maybe it's not sufficient. Maybe we can use others such as CNN, RNN, or LSTM. So that's all for my part. Thank you. Any question?
Thank you very much, Dirmanto. Is there any question in the room? Yeah, one over there. Just wait for a mic.
Sorry. Okay.
Do you think if you are doing implementation on a 64-bit microprocessor, the 30 bits,
I-
you get memories up to 64? Do you think you are accuracy more?
I think it might be, yeah, we haven't investigated further, but yeah, I think we just probably need a more training data to perform the classification. Yeah, but we have to investigate that.
We have time for one more question. Yeah. A question over there.
Yes. Yes, so have you tried servers from the same family or Google Cloud servers?
Sorry.
Have you ever used the server from the same family?
Which family?
Medicine.
Not yet. And not yet. I think.
So maybe, yeah, maybe you can meet at the coffee break. There is one question just there.
I think we did consider ASCA and SASCA. I think the details more on the paper. I didn't remember much about the detail. Sorry about that.
Okay, let's thanks again, Nirmanto. So I'll introduce the fourth and last talk for this session. So it will be about, nice to meet you. It will be about side channel expectation maximization attacks, and it will be given by Julien Beguino.
So this presentation is about side channel expectation maximization attack. And this is a joint work with Dr. Wei Cheng, Professor Sylvain Guillet, and Olivier Rigaud. So we will consider a device that is performing cryptographic operations with a SBOC and protected with a first order masking countermeasure. And the attacker will have access to electromagnetic leakages. So to dive into the state of the art, we need to have three distinctions for the different distinguishers. So it will be said to be supervised if it has access to the rule information it needs in the profiling phase, for instance, the values of the mask, the values of the key, and so on. Profiling phase means that just prior to the attack, the distinguisher has access to a database with traces. And a parametric attack is an attack where you regress parameters before performing the attack. So there are already many attacks in the state of the art, namely the template attack, which is the most effective one when you can do a profiling. When you cannot do profiling because you do not have access to the values of the mask, for instance, you can use profiled expectation maximization as suggested by Lemke and Al. When you cannot do profiling at all, there are three main distinguishers: the second order correlation power analysis, the mutual information analysis on KSA. And here we try to bridge the following gap. What if we do not have a profiling also, but we want to use a parametric attack? So just for the notation, we'll consider a secret key K drawn uniformly with n bits, plain text that are supposed to be known by the attacker, random mask, IID, and sensitive variable denoted X at the output of this box, masked, as I said. And to keep the presentation simple, we consider only a bivariate leakage attack because we have a first order masking. So this is the minimum number of pairs that we need. So we don't go further, but it could be increased if you want. We consider three leakage model of the register. The first one is the simplest one, the Hamming-Weight leakage model. So every bit in the registers leaks the same way. If you want to add more peculiarities to do leakage, you can consider that each bit leaks differently. So you add a dot product, and each of the coefficients are a bit different from each other. And the last one is the quadratic leakage model, where you consider interaction between the bits. So these models are more powerful to another, because for the linear leakage model, if you keep the vector A proportional to the whole one vector, you recover the Hamming weight leakage model. And for the quadratic leakage model, if you take a diagonal matrix, then you recover the linear leakage model. And to keep all the derivations under the same hood, we'll denote all the intermediate values this way, so that if we do not precise the leakage model, we'll only precise it when it is necessary. So as I said, the most effective distinguisher was shown to be the maximum likelihood by an Eliezer, where you just take the key that maximizes the likelihood of your model, where you know the parameters A star and B star, the real parameters. But in reality, you do not know these parameters, so it cannot be performed. So you do a template attack where you have estimation, A hat and B hat of these parameters. The other one we consider in this presentation is second order CPA, when you take the key that maximizes the Pearson correlation coefficients between the model and the traces, where you took as a combination function the centered product of the two shares. So now we dive into expectation maximization for side channel analysis. It is made of two steps. So it is an iterative algorithm. At first, you initialize arbitrarily your parameter A and B. If you have a guess, it's better, because this is one weakness of EM, because it depends on the initialization. And then you perform iteratively maximization step and expectation step. You do the expectation over the mask or the parameters that you don't know about, and then you maximize the parameter once you have averaged out these things that you don't know. So this is not really explicit as it is. So we'll now derive exactly how to do the E step and the M step for side channel analysis. So to do the expectation, we need just to compute the posterior probability that the mask M is being used for the traces Q given observation Y, if you have fixed the parameters AP and BP at step P. And using base formula, you obtain this expression. So this enables to compute the expectation step, where you see that it just simplifies, and this is a minimum because I remove the minus, to a quadratic form, quadratic expression. Then we can express the maximization step for the different leakage model this time. If we have the Hamming weight leakage model, this is simple. You just compute the covariance and the variance, and you do a regression, and you see that this is the formula for simple CPA when this is not masked. So what it means, which is interesting, is that the UEM here, it averages over the mask, then you do a simple CPA, then it averages over the mask, then it does a simple CPA until there is a convergence. And actually, when you do the derivations and compute the alpha Q, if your estimations of the parameter A and B is good, then alpha Q, it means that you are learning the mask. So if you knew the mask, you will do a CPA, for instance, which has been shown to be optimal. So here, we don't know the mask, so we average over the mask, and we do CPA. We average over the mask, we do CPA, and so on. If we have a linear leakage model, this is the same thing, but we generalize the maximization. We compute the autocorrelation matrix and the intercorrelation vector, and we do a regression the same way. Though for the quadratic model, it's harder to see. So there is no closed form expression to do the maximization. So you can do a gradient-based optimizer. It can be quick because you can compute explicitly the formula for the Jacobian. So all in all, how do we proceed? First, we normalize and center the traces. Then we initialize the parameter arbitrarily, but if you can choose it, it's better, as I said. Then we compute the base posterior to do the expectation. You see this CQ here that I didn't tell before, just a trick to improve the numerical stability of the log sum x, because you have a log of sum of exponential, which can be numerically unstable. So this small trick improves the numerical stability. And then the M step. And you see, I told you earlier that you can increase the order of the attack if you want. And here in this for loop, I equal 1, 2, you can choose whatever bond you want. So if you have, let's say, P shares, you can do the loop for I equal 1 until P, and maximize for each of the shares your leakage coefficients until you have convergence. And you can even choose different leakage model on the different shares that we did on the simulations. And at the end, you pick the key that maximizes the goodness of fit. Now I come back to the PEM that I told you about in the introduction. Know that you know what EM is. And the idea is to use the EM to profile a template for each key hypothesis. So the difference with our attack is that you need a prior data set to do a template attack. And this is useful when you have a data set, but you don't know the mask. While our attack is interesting when you do not have a data set, or if you attended yesterday's deep learning based SCA tutorials, when there is no transportability, that means you cannot train a model on a clone device and say that this is exactly the same model for another device. So here are the numerical evaluations. And what we did to see if it was interesting to use the linear model or the Hamming weight model was to add epistemic noise. That is, we add noise to the coefficient of the leakage model, starting from a Hamming weight leakage model. If the epistemic noise is 0, you just have a regular Hamming weight leakage model. And if it is high, then you tend more and more toward a linear leakage model that is completely random. So you see that the UEM with a Hamming weight leakage model works quite well, and actually it's almost as efficient as the template attack with Hamming weight leakage model. And the UEM with linear leakage model, it works less well than the UEM lean and even the second order CP at the beginning. But at some point, we provide enough number of traces, it becomes better, but still it is not close to the maximum likelihood with a linear leakage model that you see on the corner in blue lights. And all the attacks here outperform a second order CP. This suggests maybe you see that the UM lean does not really generalize well. So to use regularization, as suggested already in ridge regression for nanoscale chip. And so we add this regulation term to see if we narrow the space that we explore, it improves the attack. And we did this with the quadratic leakage model, but even with this, the quadratic leakage model does not seem to work quite well with the UEM. So in this case, we suggest to use instead the UEM AM that performs better. Because here you see that it's even outperformed by second order CP. Now we compare it with profile DM. So you need to know two number of traces for PEM, because you need to know how many traces for the profiling and how many traces for the attack. So QP here is the number of traces for profiling for each key hypothesis. So here, as we target a present S box with 4 bits, that means we have 16 times QP traces for training a model. And you see that it outperformed the UEM. So if you can do the profile DM, do the profile EM, it's better. And it rapidly, as you increase the number of QP, it rapidly increases towards the maximum likelihood. And it generalizes better. It does not suffer from this kind of other fitting effect that we face. One limitation for the PEM compared to our UEM is also transportability, because if you have prior data from another device, but it's not a mismatch, then PEM is outperformed by UEM because UEM is not affected by mismatch because there is no profiling. And finally, we applied these attacks to the DPA contest, and it worked quite well. You see that UM lean, we have the same problem. It does not really work well without regularization. A bit better than second order CPA at some point, but for less than 150 traces, not better. But if we had regularization, and if we consider here linear leakage only on the S box, because for the Hamming weight at the output just of the mask, it is very, it follows the Hamming weight model. Then it's a bit better than the UM with just the Hamming weight leakage model, but not that much. You see, it does not go that far above the maximum likelihood with Hamming weight leakage model. So UM is interesting when you cannot profile. It works quite well in terms of computation. It can be adapted to higher order attacks. You know, you add shares in the loop, and you can choose different leakage on the shares as you want. Though it suffers from kind of overfitting. So if you can do profiling, it's better. But if you can't, it's preferable maybe to try UEM. And it is also interesting when you have a mismatch. So thank you for your attention. If you have any question, I'll be happy to answer.
Thank you for the talk. We have time for some question. Okay, I'll restart. So even when profiling is available, you propose to use the UEM to deal with the portability or transportability issue. I was wondering, another solution for this problem, especially in machine learning, deep learning context. Yeah, actually, you suggest to use your methodology unsupervised to deal with the portability issue, or as you call this, transportability issue. So when you have a mismatch between your templates and your attack under device. So, well, another solution to that problem would be to perform profiling onto several clone samples in order to get a model that takes somehow into account the epistemic noise. So I wanted to ask you, do you think that this kind of approach could outperform your UEM or not?
I think that if there is an underlying model that is simple enough, it could outperform the UEM if you have enough clone devices, though it will require more computations. And I think it also depends on the mismatch. If it is, if all the clones are quite similar with some difference, then yes, this will work. But if there is really a mismatch between the devices, UM will perform better. So I think it depends on the use case.
Thank you. Is there any question in the room? In the chat, neither. How do you think UEM would compare with non-parametric methodologies such like mutual information analysis?
Yes, that would be interesting to compare. I think they will compare quite well. But the issue with non-parametric attack is that they need more traces, for instance, to avoid empty bins and that kind of thing. So I think non-parametric attack will deal better when you do not have a precise idea of the model. But UEM, I think it's better if you know that you have a linear leakage model, for instance. It's better to use it because in statistics in general, it's easier to do parametric statistics when you have a parametric
of course. Thank you. Wow, we saved 6 minutes. Not a question from there. Well, I ask you another one. Huh? I remarked that, well, maybe yesterday Stephen Pichek answered that question, but I wanted to ask you the same think. You clearly dissociated in your paper two terms that a lot of people in our community use as synonyms, which is profiled and supervised. May you explain the difference between these two terms in your work?
Sure. What I mean is when profiling, it means that you have prior data to learn a model. Unsupervised means that your pre-data are labeled. So you know all the intermediate values, for instance, the mask. In this respect, the PEM already existing in the literature is profiled but non-supervised, and our attack is non-profiled, non-supervised, and template are profiled, supervised.
Thank you very much. So we can thank you, Julien, again. So this closed the first session. Let's keep in mind that the second session will start at 10:50. And keeping that in mind, in the meanwhile, enjoy the coffee break.
Okay. I'll put the Lattice layer outside, it's fine.